two identical circular loops P and Q, each of radius R and carrying current I and twice I, are lying in parallel planes such that they have common axis. The direction of current in both the loop is clockwise as seen from O, which is equidistant from both loops. Find the magnitude of net magnetic field at point O. So we are asked to find the magnitude of magnetic field, that is total magnetic field at point O due to loop P and Q. So I'm writing, okay, let BT, this is in magnitude, okay. This is total magnetic field at point O due to loops P and Q. So we have this, okay, and we can see from the question, okay, we have identical loops P and Q having radius R, okay, and they are separated by distance twice R, and this is the common axis, and O is a point on the axis which is at equal distance from P and Q, and loop P is carrying current I and loop Q is carrying current 2I. And from question, okay, when we observe from point O, okay, so I'm writing in short, when we observe from point O to loop P, then we find current I in loop P is flowing in clockwise direction. So we have this. In same way, when we observe from point O to loop Q, we find current twice I in loop Q is flowing in clockwise direction. So we have this. Sorry. And in order to solve this numerical problem, we use this concept, okay? Magnetic field at a point on the axis of circular loop carrying current. So we have a circular loop carrying current I, and R is the radius of the circular loop. And this is a point, okay, where we are interested to find the magnetic field. And the point is at X distance from the center of the circular loop. And this is the required expression for magnetic field at this point, okay? So B equals mu naught N, which is number of turns, I current, and square of the radius of the circular loop divided by 2 bracket R square plus X square whole power 3/2. Now, let us understand this question, okay? So we have this. We have two parallel planes, okay? So we have this, and we have identical circular loop P and Q, okay? And P is carrying current I and Q is carrying current twice I. And this is the common axis, okay? So we have this, and O is the point on the axis which is at equal distance from P and Q. So we have this. Now, from question, okay? When we observe from O to P, then we find current I flowing in clockwise direction. In same way, when we observe Q from O, then we find current twice I flowing in clockwise direction. So we find this. Now, we need to find, okay, so I'm writing over here. We need to find the magnitude, okay, and direction of magnetic field at point O due to current carrying loops P and Q. And we use this expression, okay, to find the magnitude of magnetic field. And in order to find the direction, okay, of magnetic field, we use right hand, we use right and thumb rule. So in order to find the direction of magnetic field at point O due to loop P and Q, we use right hand thumb rule. And in order to find the magnitude, we use this formula. Now, let us find the direction of magnetic field at point O, okay, due to loop P. So we have this. This is point O, and current is flowing in clockwise direction, okay? So when we observe from this side, then current I is flowing in clockwise direction. So when current is flowing in clockwise direction, okay, then from right hand thumb rule, magnetic field, okay, magnetic field at this point due to loop P is directed towards coil P. So we have this, okay, magnetic field at point O, okay, magnetic field at point O due to loop P is directed towards P. So we find this. So we find this. So this is the direction of magnetic field when current in this loop is in clockwise direction, okay, when current is in clockwise direction. So we have this. Next, now when we observe, okay, from O, when we observe from O to loop Q, then from question, okay, current is flowing in clockwise direction. So current is flowing in clockwise direction. So if current is flowing in clockwise direction, then from right hand thumb rule, magnetic field at point O due to current flowing in clockwise direction in coil Q is towards Q. So we find this. So current is flowing in clockwise direction. So using right hand thumb rule, okay, magnetic field at point O due to coil Q is directed towards Q. So we find this. We find magnetic field due to coil Q at point O is directed towards Q. So we have this, okay? So I'm erasing this. So I'm writing, let BP and BQ be the magnetic field at point O due to loops P and Q. So we can see, okay, we find BP at point O is directed towards P. In same way, we find BQ at point O is directed towards Q. So we can see from this figure, okay, BQ and BP, they are acting in opposite direction. So we have this. Now, we need to find, okay, find the magnitude of BP and BQ. So as I said earlier, we use this concept in order to find the magnitude of magnetic field at point O due to coil P and Q. So we have this, okay? So I'm writing in this way. We can see we have this. This is O and this distance, okay, is twice R and O lies on the axis. So this distance is R and the radius of the coil P and Q is R. So we have this, okay? And it is carrying current I, and it is carrying current twice I, and the number of turn is 1, okay? The number of turn is 1. So BP equals mu naught, N is 1. So I'm writing in this way. Mu naught, N is 1. So let me write in this way. I, current, and square of the radius of the circular coil, P, divided by 2 bracket R square plus this again, okay, R square whole power 3 by 2. And we know it is directed towards So we have this. Clear? So we can write and this way mu naught I r square 2, and we have 2r square whole power 3 by 2. So let us simplify this. Mu naught I r square by 2, and we have 2 power 3 by 2, and we have r cube. Clear? We have this. Now, what we can do is that, okay, so I'm writing in this way, okay, mu naught I r square by 2, and we have 2 and 2 power half. Okay, so when the base is same, the power adds up. So we get this. Okay, so I'm writing in this way, and we have r cube at the denominator. So this cancels out. So we get mu naught I by, this is 4, and this gives me under root 2, and we have r. Therefore, we can write, okay, magnitude of magnetic field at point O due to coil P carrying current I equals mu naught I by 4 under root 2 R. So we have this. Clear? We have this. Clear? So as I said earlier, we are using this relation in order to find the magnitude, okay, at point O, which is lying on the axis of P and Q. So we have this. So let's call it equation 1. Now, in same way, okay, in same way, let us find magnitude of BQ. So now we have BQ equals mu naught, and number of turn is 1. And remember, current in coil Q is twice I, okay? So we have 2I, and radius is same. So we have R square divided by 2 bracket R square. So R square, so this distance, okay, R, and we have this distance R, so plus R square whole power 3 by 2. Now let's simplify this. So we have 2 mu naught I R square by 2, and we have 2 R square whole power 3 by 2. So we have this. Now, I'm writing in this way, okay, twice mu naught. I can cancel this 2 at the numerator and denominator also. 2, and I'm writing in this way, okay, because this, when the base is same, the power adds up to give 2 power 3 by 2. So we have this. And we have R cube. So this cancels out. Now, let me cancel this. So finally, we get BQ equals mu naught I by 2 under root 2 R. So we have this. Let us call it equation 2. So we have this. And we know direction of BQ at point O is towards Q. Now what we find looking into equation 1 and 2 is that BQ, okay, is greater than BP. So we find this. Okay, we find this. Now, we have this, okay? I'm rewriting equation 1 and 2. This is mu naught I by mu naught I by 2 under root 2 R. Okay, this is equation 2. Let's see. Mu naught I 2 under root 2 R and BP is mu naught I 4 under root 2 R. So we have this. And what we find, okay, is that BQ and BP, they are acting in opposite direction, okay? So this is in magnitude. So I'm writing in this way, okay? And we know this, okay? As I said earlier, so we have this condition. So resultant or total magnetic field at point O is BT, okay? So I have supposed this earlier, okay? Therefore, BT equals BQ minus BP. And the direction of resultant magnetic field is towards, okay? So I'm writing over here in vector form, okay? BT is directed towards BQ. So we have this. So BT, that is resultant magnetic field, act towards coil Q. So we have this. So let's find this, okay? So BT equals BQ and BQ is mu naught I by 2 under root 2 R minus mu naught I by 4 under root 2 R. Now we can take this common, okay? So we have 1 by 2 minus 1 by 4. So let us do simplification, okay? Therefore, net or total or resultant magnetic field at point O due to coil P and Q is BT equals mu naught I by 4 under root 2 R. And as I said earlier, okay, it is directed towards coil Q. So we have this.